Welcome, everyone, to the first session this morning. So the first talk will be about quantum key leasing. And, sorry, what was your name again?
I'm Justin.
Justin will give the talk in replacement.
Yeah.
Please start.
Yeah, unfortunately, none of the authors were able to make it, but it's a really great paper, so we couldn't let it go unpresented. So let's get started. OK. Seem to be having a little bit of technical difficulty. Perfect. OK. So in the quantum setting, we have this notion of unclonability of quantum information. Given a state, you cannot generally make two copies of it. Now, this is great because we can have states that are unclonable. But we might want to have more general functionalities that are unclonable, such as programs. So you can imagine that we encode a program as a quantum state, and then you can evaluate the state to evaluate the program. Then we'd like it so that you cannot copy a state that evaluates the program. So if you make two different states, at least one of them should not be able to evaluate the program anymore. Unfortunately, there's some pretty strong impossibility results for general copy protection. And all the positive results either need non-standard assumptions or are for limited functions only. So for example, if we want to copy protect interesting functions, we need classical oracles or maybe post-quantum I/O. And if we use standard assumptions, we're limited to things like point functions. There's this new notion called secure key leasing, where the idea is to try and obtain unclonable programs with more advanced functionalities for more standard assumptions. And it uses a slightly different notion of unclonability that I'll cover in just a moment. But as before, we're going to encode our state, our program as a quantum state, and then you're able to run the state to run the program. And in this particular work, we're going to be concerned with specifically with decryption states. So we're going to lease out a key, a decryption key as the program, and then using the state, you can decrypt ciphertexts. Now, the notion of security we want is that after returning the state, the lessee should have no capability of computing. This is a little different from the prior setting because instead of having two copies that should be evaluatable, we want one of the copies can be is returned and can be checked. So it must be actually the original state. And then if it is the original state or otherwise passes the verification procedure, then the other state should not be evaluatable, even with any arbitrary evaluation procedure. So this can be widely applicable. For example, you can imagine that you have a key that lets you decrypt some streamed videos from Netflix, and eventually your subscription expires, and they ask you to delete your key. Or maybe you want to temporarily give a key to a server for evaluating something, and then you want to ask for it back. A more ambitious goal is to make all this communication classical. So before, we had this quantum state that was sent from the lessor to the lessee, and then we can do what we did before. But can we set up everything on the lessee's side just using classical messages from the lessor to the lessee? Then the second piece of this is, can we make the returned program, instead of returning the program as the original, can we generate a classical certificate for this? Now, if we can do both of these two things, then all of the messages between the lessor and the lessee become classical. And in general, we might even hope to have all of the lessees, or all the lessors' computation become classical. There are a couple of prior works which studied secure key leasing, but unfortunately, none of them achieved a fully classical lessor. A couple of them did achieve classical revocation, but they used pretty strong assumptions like a new conjecture or I/O. In this work, the authors construct a secure key leasing scheme for both PKE and unleveled fully homomorphic encryption, and specifically with a classical lessor. So all messages in this protocol are going to be classical. And we can see here that we now fill out both columns with an affirmative. Now, I would like to mention very briefly that getting unleveled FHE has some technical barriers. You should see the paper or ask the authors about the details for that. But getting unleveled FHE with secure key leasing is an open problem. Okay, so the main thing about this is that it's kind of a best of both worlds result, where we get secure key leasing with a fully classical lessor, and you do it with more standard assumptions. Okay, let's go into the syntax. So the lessor is first going to start off by publishing some master public key, and the lessee can use this to generate their own public key and secret key state. And then they can register the public key with the lessor. You can think of this as maybe the lessor signs the public key. And now, of course, if you encrypt something under the new public key, then the key is able to decrypt it. And specifically, since we require 1 minus negligible correctness, by gentle measurement, this doesn't really disturb the key state, so you can keep reusing it to decrypt more and more messages. In terms of security, what we want is after this initial setup procedure, the lessor might ask the lessee to delete the key. And the lessee can run some procedure which generates a classical certificate. And let's say that this certificate is accepted by the lessor. In this case, what we want is that whatever state that the lessee still has should not be a good decryptor, in the sense that if you give it a fresh ciphertext, that ciphertext should have semantic security. We could also extend to the more general case where the lessee does not necessarily return a good certificate by just aborting in the experiment if the certificate is invalid. So now we handle lessors which maybe with some probability fail to generate a false certificate. So let's talk about how to make a quantum decryption key. There's a pretty simple idea from prior work, which is just to use 2 keys in superposition. And specifically, we want these 2 keys to decrypt correctly with respect to the same public key. And so if you decrypt in superposition, you'll get the same result in both cases, and so you can measure that without disturbing your state. But how do we generate this key with just classical communication? Because not a lot of states have that structure that enables them to be generated without knowing a classical description of these 2 secret keys, which intuitively have to be related somehow. The authors draw some inspiration from protocols between a classical client and a quantum server, specifically classical verification of quantumness or quantum computation. At a high level, the authors are going to make a combination of lattice-based encryption with lattice-based proof of quantumness protocols, with some asterisks here. They're going to have to modify the protocols a little bit because they achieve some very slightly, they need some different properties. I'll go into that in a moment. Specifically, if we look at the proof of quantumness protocols, we want something which a quantum computer can do almost all the time, but a classical computer can never do. So we need quantum completeness and classical soundness. Here, we want something, the security against a quantum adversary. So we need quantum soundness. So the idea here is we're going to set up a scenario where the verifier is going to send some function, and using some quantum tricks, which I'll get into in a moment, the prover, or the lessee, is going to generate a superposition over preimages of some y. And then they'll send y back to the verifier. Then the prover, or the lessee, is supposed to send back both one of the preimages and a measurement of the secret key in the X basis, or the Hadamard basis. Now, this differs from prior work because if you look at the proof of quantumness protocol, it actually asks for one of these at random. Here, we want both. And we're able to show that no QPT prover can successfully generate both of these with probability much better than 1/2. So the next step is, of course, now we want to use x0 and x1 as the decryption key. And the observation is that the BCM Plus protocol has some very strong relation to LWE. And so they design a variant of regev encryption, which allows 2 different keys, and in such a way that you can generate this superposition. If you want to see the details, you should take a look at the paper. OK. So I'm sure you've all seen LWE before, but just as a quick reminder, we have some matrix A, and given A and SA plus E, the search version is defined S. The decision version is to distinguish between SA plus E and a random B, with A also being included in the output. If we open up that protocol from before, what we're going to do is we're going to set up, the function is going to be A and some SA plus E. And then the way that you evaluate this function is you matrix multiply it by your input. So if we were to multiply it by, say, 0x0, this would be SA plus E times x0. Yeah. And you can notice that if 0 and 1 are related by S, then it's very approximately a collision. There's some, and if you add a smudging factor, some error, then you actually do get a collision. And so now you can generate this intermediate state for the secret key 0x0 plus 1x1. OK. So now the trick to this is we're going to set the master public key to be the function. To generate a public key, you generate the some image of the function, and along with the secret key. And again, if you want to see the details of how you can actually use this to decrypt, you should see the paper. But the idea is to check whether or not this is deleted, or rather to delete, you just measure in the X basis or the Hadamard basis. And now this will give you a certificate that is related in some way to S, which we saw on the previous slide is kind of what gives you the collision. So they'd like to do a reduction directly to quantum soundness, but unfortunately, quantum soundness is not quite good enough. And the issue here is that in this particular protocol, half of the certificate, or half of all strings are valid certificates. So a simple fix to this is to use parallel repetition. And now even if the adversary guesses the certificate, it would have to guess all the instances. Unfortunately, there's some issues with parallel repetition and fully homomorphic encryption. The second issue is the extraction, because we need to get both a z-basis measurement, and we also have to get that certificate. And that's where a lot of the technical work comes in. I'm running a little bit short on time, so I might skim over this a little bit, but this is a really interesting part of the paper. And essentially what you have to do is, assuming that you get a valid certificate, the leftover state is a good decryptor. So now you need to use this state to extract x0, x1. So they use a regev-style LWE search decision reduction, but the issue is that the decryptor can be an unclonable quantum state, so you can't necessarily do things like guess and run multiple times, because every time you run the decryptor, you might disturb the state. So they built some new quantum rewinding techniques that are specific to this setting in order to construct a quantum version of the search to decision algorithm. Okay. And the key idea is to keep the LWE decision adversary undisturbed after it's tested every time. You should check the papers if you're interested in the details. Thank you for listening. And I might not be the best person to answer questions, given that I'm not the author, but I will do my best if you have questions.
Do you have any questions?
Thank you for your talk. So I think you want to remotely generate a superposition of two secret key over classical channel, and why just you don't use a remote state preparation in black box way?
Right. So remote state preparation protocols are generally for specific structured states. Like, we want to generate a coset state, we can do that. If we want to generate a BB84 state or a Wiesner state, we can do that. Here we want to generate a superposition over two particular states. So it just doesn't quite have the structure that prior remote state preparation protocols have allowed you to generate.
Then how about blind computation, blind quantum computation? You can generate any state remotely.
Sorry, one more time?
Blind quantum computation.
Blind quantum computation. Not certain on that, but from what I recall, blind quantum computation is more about, it might consume the state, whereas here we want to have the state at the end of the protocol.
Okay.
Yeah.
Okay, another quick question. Great, then we're well on time. Let's thank the speaker again.
Okay.
15 minutes. Okay, the next talk will be about also key leasing, this time simple. And Tomoyuki will give the talk, please.
Okay, thank you for the introduction. So this is a joint work with Fuyuki Kitagawa and Takashi Yamakawa. So by the way, I don't know why this session is called Verifiable Deletion, not quantum session. Okay. Okay, so this is key leasing, and the previous speaker already explained this key leasing. So in key leasing, a company has some secret key, and this company wants to lease key to Alice. And by using this key, she can do several functionalities. For example, she can decrypt ciphertext of PKE, or she can evaluate function of PRF, or she can sign message in digital signature scheme. But to some point, this company wants to make sure that she can no longer use this functionality. So for example, she can retire from this company, and the company now wants to make sure that she can no longer use this functionality. Okay? And a standard approach in classical cryptography is a key updating. So this means a company updates the key. So company issue new secret key and public key and distribute this new public key all over the world. But this approach has several disadvantages. For example, this is very costly because company must issue many new keys and the company must distribute this new key all over the world. This takes much cost. And also there is an issue of time lag, which means although key is updated, but still someone can use old key for some time period. So in this way, this key updating is not the complete solution for this key leasing. And the question is key leasing without key update possible? In the classical case, this is not possible. But interestingly, by using quantum, this is possible. And already there are several prior work to construct this quantum key leasing. And so this secure key leasing is a task that can be achieved by using quantum. So now secret key is a quantum state, and this key is leased to Alice. Then by using this quantum secret key, Alice can do several functionalities like evaluation of PRF or signing a message. And once the company wants to revoke this quantum key, she returns this quantum key to the company. And the company has some verification key, and by using this verification key, company can check whether this quantum key is correctly returned or not. And if this is accepted, the company can guarantee that Alice can no longer use this functionality. So this is a secure key leasing. And in particular, in this talk, we focus on secure key leasing with classical revocation. So this means a classical secret key is leased to Alice, and when they want to revoke the key, Alice measures this quantum state in certain basis. And Alice issues some classical certificate, deletion certificate, and this deletion certificate is returned to the company. Then company, by using the verification key, check this deletion certificate, and if this is accepted, again, company can guarantee that she can no longer use this functionality. Okay? And by the way, one difference from the previous talk is this is not fully quantum. So the first initial quantum secret key is sent over quantum channel, and later revocation is only classical. While in the previous talk, everything is classical. Okay, and we have three contributions. So first, our contribution is introducing a new unified and simple framework to construct cryptography with secure key leasing. And this simple framework is based on certified deletion property of BB84 states, which I explain later. And our second contribution is based on this simple framework. We construct PKE, PRF, and digital signatures with this classical revocation. And our construction have several advantages over previous constructions. And finally, we introduce a new security notion, which we call verification revealing attack security. So intuitively, this means after the certificate of deletion is accepted, then the verification key is revealed to the adversary. And still, security is guaranteed. And as far as I know, all previous constructions are totally broken in this setting. Okay, so first I explain the first contribution. So some unified and simple framework. And this is based on this certified deletion property of BB84 states. Okay. So this is a certified deletion property of BB84 states. So we have adversary and challenger. And the challenger choose random bit strings. And based on this random bit, challenger generates a random BB84 state and sends this to the adversary. the adversary must return some bit string, y, and then challenger reveals information of all bases, so computational basis or Adamar basis. And also challenger reveals all information of bit value of Adamar basis states. And after that, adversary must return another bit string, z, and security requires this property. So this means, so all yi should be equal to xy for all I such that theta I is equal to 1. So this means for each Adamar basis, the bit value should be the same. And also all zi should be equal to xi for all I such that theta I is equal to 0. So this means all computational basis value should be the same. Okay? And the probability that such event occurs is exponentially small. So this is just a statistical statement based on the property of quantum physics. So intuitively, if you want to get correct value for Adamar basis, you have to measure all qubits in Adamar basis, because you don't know which state is Adamar basis or computational basis. But in that case, you destroy the information of a computational basis states, and then you can no longer get the information of computational basis. Okay? So that's why you cannot satisfy both property at the same time with high probability. Okay, so this is a certified deletion property of BB84 states. And based on this, we construct a PKE, PRF, and digital signatures that satisfy secure key leasing with classical revocation. And also, this construction satisfies our new security notion, verification revealing attack security. So now I explain this second contribution and third contribution. Okay. And unfortunately, because of the time limitation, this time I only explain construction of PKE. And for details of digital signature and PRF, please see the full paper. Okay, so first I explain the syntax of our PKE secure key leasing with classical revocation. So like the standard PKE, we have three algorithms: keygen algorithm, encryption algorithm, and decryption algorithm. And the difference is a keygen algorithm output a secret key, which is quantum state, and also this keygen algorithm output classical deletion verification key. Okay? And also, in addition to these three algorithms, we have two extra algorithms. One is a deletion algorithm that takes quantum secret key as input and output classical certificate. And the deletion verification algorithm takes classical deletion verification key and classical certificate as input and accept or reject. And like the standard PKE, we require the decryption correctness, which means that the correctly generated ciphertext is correctly decrypted. And in addition to that, we require a new property, which we call deletion verification correctness. So this means if the certificate is correctly issued, then this certificate is accepted with high probability. So this is the correctness of certificate deletion. And security, which we introduce here, is the VRA security. So this is defined as the following security game. So we have adversary and challenger. And the challenger first generates key pairs: public key, secret key, and deletion verification key. And the public key and quantum secret key is sent to the adversary. And adversary must issue certificate that show that this quantum secret key has been deleted. And in addition to that, adversary output to challenge message, because this is indistinguishable security. So adversary issue to message, M0 star and M1 star. And then this challenger check whether this certificate is a correct one or not. And if this certificate is correctly accepted, then the challenger encrypt one of the two messages randomly and send challenge ciphertext to the adversary. And also here, the challenger now reveals the deletion verification key. And on the other hand, if this certificate is not accepted, challenger doesn't do anything. And finally, the adversary must guess the correct bit B. So adversary must guess which message is encrypted. So this is just a standard indistinguishable security. And the security means the advantage of winning this game is just negligible, at most negligible. So this is a definition of in the VRA security. And so I also quickly explain construction. So our construction use only generic Indo-CPA secure PKE scheme. And key generation algorithm of our scheme output bit strings, random bit strings x and theta, and also outputs many classical PK and SK. And secret key is very similar to the previous talk. So this is a superposition of two secret key. So if theta I is equal to 0, this is not a superposition, just one single classical SK. But if theta I is equal to 1, then this is a superposition of two secret keys. And public key is just a pair of all classical public key. And also deletion verification key is information of basis, information of basis, theta, and also information for all x and sk prime for the other mal basis. And so encryption is just the same. We encrypt each message one by one by using classical public key. And for decryption, just we measure secret key and get the classical information of SK, and by using this SK, we decrypt. We learn the original classical decryption algorithm. But actually, by using the gentle measurement lemma, we don't need to destroy this quantum state. Just we can do this decryption algorithm coherently. And deletion algorithm measure all classical secret key in other mal basis and get measurement result, which is a classical deletion certificate. And deletion verification algorithm check whether this measurement result satisfies this property. So if the SK is a correct quantum state, if this is correctly measured in the other mal basis, the result satisfies this property. Okay, so in this way, we can construct PKE, secure key releasing, with classical revocation from Indo-CPA PKE. And the previous construction is quantum revocation from general PKE or classical revocation from LWE. And compared with the first result, our revocation is classical one, which is our advantage. And compared with the second one, their assumption is based on LWE, but here our assumption is a generic PKE. And so I cannot explain details here, but we have also constructed a PRF secure key releasing with classical revocation, only from the assumption of one-way function. And previous construction assumed LWE, so our assumption is much weaker than previous construction. And finally, we have also constructed digital signature secure key releasing with classical revocation. And compared with previous construction, our signing key is a static one. So this means in the previous construction, every time I sign message, the length of signing key is increased. But here, the signing key is not changed every time I sign message. Okay, so in summary, we have three contributions. And the first contribution is we have introduced a new unified and simple framework to construct cryptography with a classical secure key releasing. And this is based on the statistical property, so-called certified deletion property of BB84 state. And second contribution is a construction of PKE, PRF, and digital signatures with classical revocation. And our construction have several advantages over previous ones. And finally, we have introduced a new security notion, which we call verification revealing attack security, which roughly means once the certificate is accepted, the classical verification key is revealed to the adversary. But still, security is guaranteed in this setup. And as far as we know, all prior constructions are totally broken in this setup. Okay, so thank you very much for the attention.
Thank you. Do you have any questions?
Dominique, thanks for a nice talk. I have a question that you say that with gentle measurement lemma, the secret key cannot be destroyed during the decryption. Could you explain that in more detail why we can apply gentle measurement lemma there?
Yeah, okay. So because the original classical PKE has correctness, which means correctly encrypted message is correctly decrypted with a high probability. So probability at least 1 minus negligible. And in this case, so gentle measurement lemma means that if your measurement result is very large, then you don't disturb your state. So now your measurement result is just a correct decryption message with probability at least 1 minus negligible. So this means you don't disturb state, secret key state, except for the negligible probability.
Yeah. So you mean that if the ciphertext is correct, can be decrypted correctly, then the secret key will not be destroyed.
Yeah.
Okay, thank you.
Any further questions? John?
Just a quick question. You said that all prior constructions are totally broken under the VRA security notion. Is it kind of easy to fix them to be secure, or you haven't, or it's not clear how to fix them, or you haven't looked at it?
Yeah, so, okay. So this is a good question. Actually, I haven't checked all the previous construction, whether we can easily recover their security. So maybe I will check.
We still have time for a bit of questions, if there are any. I have one question. So compared with the previous talk, one big difference is that in your case, the key distribution needs to be quantum. Do you think, how difficult do you think it would be to make it classical, maybe with techniques from blind computation, or do you think that wouldn't work?
Okay, yeah. So actually, I had that similar question to the previous talk, and so I think I haven't checked, but I think by using blind quantum computation, we can remotely generate a superposition of this secret key in such a way that the adversary cannot learn which state is generated. So I think maybe we can use classical channel instead of quantum channel to remotely send this quantum secret key. But in that case, maybe assumption should be stronger than the current one. So as far as I know, currently we need some, for example, classical FHE plus some assumption or some dual mode trapdoor function to realize blind quantum computation. But while here, what we need is only general PKE or one-way function or just LWE. So yeah, so I think maybe we can change quantum channel into classical case, but the problem is in this case, assumption becomes much stronger.
Okay, thank you very much. So let's thank the speaker again. So you have 60 minutes. There may or may not be the timer starting, but I have these sheets.
Okay, cool. Okay. Are you going to introduce me, or should I?
Yes,
Okay.
sorry, I was distracted.
It's all good.
Yeah. So the next talk is about secret sharing with deletion, and Ben Sela is going to give the talk. Please.
All right. Thank you for the introduction. This is joint work with Jonathan Katz, and I'll start by just comparing the notion of deletion that we consider here with what we've seen in the previous two talks. So with secure key leasing, we saw how you can encode the ability to evaluate a functionality in some quantum state, and then at some point you measure the state. This destroys your ability to evaluate the functionality and hopefully also produces some proof that this is the case. In our case, we'll think about encoding some classical string into a quantum state, and then at some point you can delete this string by measuring the state, and the hope is that whatever's left over after measurement, it's impossible to extract the string that was originally encoded. And also, hopefully, we get some proof that this is the case. So the simple picture that we usually consider is some user uploads their data to the cloud, and they encode it in an appropriate quantum state. Later, they'd like the storage provider to delete their data, so they ask for the data to be deleted, and they ask for proof that this has been done. The storage provider applies some suitable measurement and provides a certificate, which can then be verified. So we can consider a privately verifiable deletion, where the verification algorithm, the verification key, has to be secret for any deletion security guarantees to hold. And we can also consider publicly verifiable deletion, or PVD, where any security guarantees for deletion hold even if the verification key is published and in particular is available to the adversary. So some consequences of this: any third party can verify deletion proofs, not just the party that delegated the data. And you also don't need to store your verification keys securely in this setting. So now we'll talk about how this can be applied to the secret sharing setting. So first we'll quickly recall the definition of classical secret sharing. We have a set of authorized sets, which we call an access structure. Share splits a secret into a set of shares, and then a reconstruction algorithm takes an authorized subset and gives back the secret. And security just says that an unauthorized set of shares does not leak information about the secret. So a recent work that appeared at Crypto last year first initialized the study of secret sharing in the certified deletion setting. And so we'll present some of their definitions here. So first, we update the syntax for a secret sharing scheme. The shares now have to be quantum so that we can delete them. And additionally, the share algorithm outputs a verification key. Reconstruction is about the same, and now we have a deletion mechanism where we can delete any of the shares, and to go with that, we have a verification algorithm that can verify proofs of deletion, output by the delete algorithm. They also introduced a security definition, which they call adaptive certified deletion. And it works roughly as follows. First, we generate our quantum shares and verification key for some secret. And now the adversary is allowed to adaptively alternate between corrupting and deleting shares. And they can do this in any order that they'd like. However, they are constrained in the following way. The set of shares which the adversary has corrupted but not deleted, at no point in this experiment can that set be an authorized set. At the end of this process, the adversary outputs their state, and we can consider a computational notion of security, which just says if the adversary is bounded in this experiment, then the state the adversary outputs at the end computationally hides the secret that was shared. We can also consider a slightly stronger notion, which we call everlasting security. We still require that the adversary is bounded during this experiment, and in particular when it outputs deletion proofs. But if this is the case, the security notion says that the state of the adversary at the end, information theoretically hides the secret. Meaning if you have a bounded adversary participate in the game, and then later an unbounded adversary tries to take what's left, they still won't be able to determine what secret was shared. So now I'll just give a quick overview of the prior results. So they actually introduced two notions of security, which happen to be incomparable. The first they called no signaling certified deletion, and the second we just discussed, adaptive certified deletion. They additionally give constructions satisfying each of these notions with privately verifiable deletion proofs. And additionally, their constructions were secure against an unbounded adversary. So to see where we jump off from this, just to summarize, both of their works were only secure in the publicly verifiable deletion setting, and additionally, their adaptively secure construction only worked for threshold access structures, whereas their no signaling construction worked for general monotone access structures. So we make progress in all of these directions by giving constructions that satisfy both notions of security, have publicly verifiable deletion proofs, and additionally, in both cases, work for general monotone access structures. And just in a little bit more detail, we give two constructions satisfying the adaptive notion of security. One is based on the existence of a one-way function, and the other requires the slightly stronger assumption of LWE, but in this case, we get away with a smaller number of qubits to encode each share. And the third construction we really just include for completeness, since it's actually the same construction as was presented in the prior work, but we just note that given a sub-exponentially secure one-way function, it can be upgraded to satisfy publicly verifiable deletion as well. In this talk, we're going to focus primarily on construction 1 and maybe mention construction 2 a little bit. Okay, so as our starting point, we will recall a technique introduced a few years ago for encoding a single bit in such a way that it can be deleted in a publicly verifiable manner. So we start with a one-way function, and to encode a bit, we'll sample 2 strings and encode it in the phase of this state here. And for the verification key, we'll simply publish the evaluations of the one-way function on each of the 2 strings. If we want to extract this bit, we additionally need the XOR of the 2 preimages. And given that plus the state, we can measure the state in the Hadamard basis and multiply the results by the XOR of the preimages. To delete, we can measure the state in the computational basis. This gives one of the 2 strings x0 or x1. And then to verify a certificate, we just evaluate the one-way function on the certificate and check that it maps to one of the elements in the verification key. And security basically says that if you give this state to an adversary, but the adversary does not know the preimages, then if the adversary is able to output one of the preimages, i.e. a verification key or a certificate that accepts, then they must have destroyed the state in the process of doing so, or destroyed any dependence on the bit B. So something interesting to note here, there's this odd relationship between extract and delete. To extract, knowledge of the preimages is required, but for deletion security to hold, it's required that the preimages are kept secret. Keep this in mind because this will become a problem momentarily. So how can we use this technique to create a secret sharing scheme where we can delete the shares? Well, we can start with a classical scheme and just encode each bit of each share using the technique I just mentioned. So we start with classical shares. For each bit of each share, we'll sample a pair of elements from the domain of our one-way function, and then we'll create the encodings of the form we just discussed. And then for the verification key, we'll evaluate the one-way function separately on each string that we sampled. To reconstruct, we use the extraction technique we mentioned to extract the classical shares from the quantum encodings. And to delete, we can just delete one bit at a time. So we can measure a share in the computational basis. This will give a sequence of, hopefully, preimages. And then each preimage will serve as a proof of deletion for a single classical bit of the corresponding classical share. And then verification, we just check that that preimage is actually a preimage of the correct element in the verification key. So, of course, I mentioned we have this problem earlier. Our ability to reconstruct is at odds with our ability to securely delete, right? So these preimages, we need to figure out what to do with them. If we want reconstruction, we have to hand them to the parties for an honest reconstruction. But if we want to be able to delete, we need to keep them hidden. So what do we do? Well, we could also secret share the preimages. So let's create a classical secret sharing of all of the preimages together, and then under the same access structure, a classical sharing of the secret. Create our quantum encodings as before, and then just throw in to each share the classical share, the corresponding classical share of the preimages. So now it looks like this maybe solves our problem, because now, recall in the adaptive experiment, the adversary is never allowed to hold an authorized set of shares. So if you don't have an authorized set of shares, the top-level secret sharing here hides the preimages, and maybe we get deletion security from this. Unfortunately, this is not the case, because an adaptive adversary that goes through and alternately corrupts and deletes shares accumulates information, because the classical part of each share is never actually deleted. And so eventually, an adversary will recover enough classical shares in the top level to reconstruct the preimages, and at that point, any future deletion proofs are invalidated. So we're going to go through a quick example of this, because it does present a way forward. So this is a 3 out of 4 scheme where each column is a share, and the top row is the classical sharing of the preimages, and the bottom row is the quantum encodings using those preimages. So we can imagine corrupting the first 2, deleting the first share, corrupting a third. Okay, now we've picked up 3 classical shares, so we can grab our preimages. Now the next deletion proof doesn't do anything, but it still passes. And now we've recovered the secret. However, the interesting thing here is any deletion proofs, in this case just the first one, any deletion proofs prior to recovering the preimages are valid in the sense that they actually correspond to properly deleting the information. So if this were a 4 out of 4 scheme, this would actually be secure because the adversary was forced to delete one of the shares of the underlying secret. So how do we make this secure for a 3 out of 4 scheme? Well, we can force the adversary to delete 2 shares by just iterating this construction with 3 levels. So in the bottom level, we have encodings of classical shares of the secret. In the middle row, we have encodings of classical shares of the preimages used to encode the bottom row. And then in the top row, we have classical shares of the preimages used to encode the middle row. And the idea is if we go through this attack again, any deletion proofs in the middle row are valid until we've recovered the preimages in the top row. And then if we keep going, any deletion proofs in the bottom row are valid until we've recovered the preimages in the middle row. And in this way, every time you learn a new set of preimages, you can kind of convince yourself that the only order you can learn them in is from top to bottom. And additionally, every time you learn a new set of preimages, you must have output another deletion proof. This is just because to learn a new set of preimages, you have to corrupt an authorized set of parties. But to corrupt an authorized set of parties, you need to intersperse at least one deletion proof into that sequence. So if we just do n+1 rows of this, every time the adversary breaks into a new row, they must submit a deletion proof, and each deletion proof will correspond to a valid deletion in the bottom row, i.e. the row that contains the shares of the actual secret. And so this should be secure for any access structure, because we're forcing the adversary to delete every single share. There's one additional problem, which is that the shares being shared at each level are larger than in the last level. But we can solve this by compressing the shares with a PRF and instead sharing a PRF key at each level. And then for our encodings, we generate the preimages as evaluations with different PRF keys. Okay, so just to summarize, in this construction, we take some classical secret sharing scheme for any access structure and a one-way function, and we obtain a secret sharing scheme with publicly verifiable deletion. And the share size is the number of parties times the size of the underlying classical share. Okay, so how do we reduce this how do we eliminate this dependence on n, the number of parties? So if we return back to our original point, the starting point was we encode our classical shares into these states, and the problem was what do we do with the preimages, right? We need them for reconstruction, but we need to hide them for deletion. So if we had an oracle that could just do the computation for us, that would solve our problem, right? We measure for reconstruction, we can measure a state in the Hadamard basis and pass the results of this measurement to our oracle, which has the preimages hard-coded. And then it computes the extraction step and then the classical reconstruction step as well. To do this, we'll use a compute and compare program, and I'll skip over a few of the details because I'm short on time. But essentially, we can instantiate the oracle with a compute and compare program, which takes these Hadamard measurement results, has the hard-coded preimages, and tries to output the secret that's reconstructed from those, and checks if it's equal to some lock value. And if we use a compute and compare obfuscator, which it's shown can be constructed from LWE. Then it turns out this gives us another instance of secret sharing with PVD. And in this case, we didn't have to use additional qubits. So I'll skip the details of that. But yeah, so summary of our second result. And again, we take some classical secret sharing scheme and we inherit the access structure of that scheme in our construction. So yeah, so here are some open problems. Yeah. May I go over them or? Yeah, okay. Yeah, so in a prior work on publicly verifiable deletion, you can use the same techniques that we used to have PVD with a weaker assumption than a one-way function. However, in our one-way function-based construction, we also need a PRF, so it's not clear how to replace the one-way function with something weaker. So that's something interesting to look at. Also, I mentioned the no signaling construction requires a sub-exponentially secure one-way function. Relaxing this requirement would be interesting. And additionally, our constructions, they have everlasting security, but they're not information theoretic. They require a bounded adversary, and this is inherent in the publicly verifiable deletion setting. So one open problem left by the prior work is privately verifiable information theoretic adaptive certified deletion for general monotone access structures. So thank you.
Thank you very much. Are there any questions? Yes, please.
I have a question about entanglement. So, in Crypto 24, a paper called Unclonable Secret Sharing, they consider the case when corrupted parties have pre-shared some entanglements. So what if, in your problem setting, the corrupted parties share some pre-entanglements?
The shares, or the parties holding the shares?
Like the corrupted parties, they have pre-shared some entanglements, and they then to attack your secret sharing with public verifiable deletion schemes.
So in the security notion that I focused on, adaptive certified deletion, this shouldn't be an issue because there's really one party that's going along and corrupting them. In the no signaling setting that they mentioned, you have independent parties, you have independent parties attacking different subsets of the shares at once.
Yeah, yeah.
And in that case, they are allowed to share entanglement. And actually, this is the reason why sub-exponentially secure one-way functions are required. I don't think you would need that assumption if you assumed no entanglement.
Yeah, okay.
But in the notion I focused on here, I don't think it's an issue.
Okay, yeah, thank you.
Okay, if there's a quick question, we can still take one. Otherwise, let's thank the speaker again.